Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. Chapter 2 is discrete time models. Section 2.4 is going to be difference equations at equilibrium. And then this lecture specifically, what we're going to do is give an introduction to the definition of what an equilibrium is for a difference equation, focusing on order 1 equations. And then we will give, in this lecture, we're going to give an introduction to stability of equilibria. But then in the next video, we're going to do in detail the stability of all equilibria. Let's do it. What we're going to do is recall first, we're going to consider, in this case, to do equilibrium and stability theory, we're going to deal with autonomous difference equations, so there's going to be no time involved in there, just the previous timestamp. In particular, this one is a first order one, and then we'll get crazier if we want after that. But for now, we're going to start with considering this first order autonomous difference equation. Whether this is linear or nonlinear, we don't know, but we get a starting point or our initial conditions, and once it's autonomous, we can view this as iterations of the function f. So we actually get a sequence. If at the first time t equals 0, x0 is some real number alpha, which we arbitrarily pick, possibly. But once we do that, we get a sequence alpha, then f of alpha, then f of alpha, then f of alpha, and then we just keep putting it into the function f so we can view this as iterations. So for notation, so that we don't have to write f of f, and you don't have to remember this is composition, so you should go look at composition videos. But we're going to use the notation alpha is just f0 of alpha, f1 of alpha is just f of alpha, and then you actually get useful notation. f2 of alpha is f of alpha, and then in particular ft of alpha is going to be the tth iteration of alpha, essentially. So once we do that, what we're going to want to do is phrasing this first order difference equation like this, which is now autonomous. We want to know, and the notion of equilibriums and long-term behavior of this difference equations is central to the study of all of these dynamical systems or difference equations. Basically, what we want to know is, what is an equilibrium going to be? It's going to be viewed this way. It's going to be a fixed point for the map. We want to know when the system stops changing over time. If we put new values into it, we just keep getting the same value. This is an equilibrium or a steady state. Nothing is happening. And we want to know if and when they happen, and then what we want to know is, depending on whether you start at different values, will your solution in the long-term behavior always tend towards that equilibrium, or will it diverge away from the equilibrium? This is what we're going to call stable or unstable, and this is what we mean by stability theory in dynamical systems, whether it's discrete or non-discrete. We're going to talk about equilibrium, and then stability theory is whether, if we have equilibriums or steady states, then we want to know if all the other solutions to that system tend towards over time to that equilibrium, or whether they diverge away, and so we're going to get stability definitions as well. Let's get to it. All right, definition. Given a difference equation, xt plus 1 equals f of xt, and a starting point, initial conditions, x0 equals alpha, for some real number alpha. A point x star is going to be called an equilibrium point, or a steady state point of this difference equation, if f of x star equals x star. What that means is, another way of saying that is, x star is, this is the definition of a fixed point. A point is a fixed point of a function if it maps it to itself. In other words, another way of saying that also is, x star is essentially a constant solution for this difference equation, because if we start with the initial conditions of starting, instead of starting at alpha, if we start at x star, then x1 is going to be f of x star, but we know f of x star is x star. So then f1 is x star, and then f2 is going to be f of x1, but we know x1 was x star, and that's f of x star, which is x star, and so f of t is going to be x star for everyone, so it's not going to change. So there's no change in this dynamical system, and this is why we're going to call it an equilibrium or steady state point. Therefore, if we plot this guy, xt plus 1 equals f of x, and xt plus 1 equals x, think of this as y equals f of x, and y equals x in the x t plus 1 xt plane. Then the equilibrium points are going to be the xt coordinate, or the x coordinate of where they intersect, where these two curves intersect each other. So if I have the xt and then the xt plus 1 plane, then if this is my curve, xt plus 1 is f of xt, some nonlinear difference equation, then I don't know how to find the closed form, but I do know how to plot that curve. And then I plot the straight line xt plus 1 equals xt, where the if and when they intersect, that value is going to be an equilibrium point. So this is going to give us a pictorial way of finding equilibriums, even if I can't analytically find the closed form solution for these. Let's do a couple examples. Or example 1, find the equilibrium points of the difference equation xt plus 1 equals xt squared minus xt plus 1. This is nonlinear also. To get interesting ones, and why we really want this is because systematically linear ones, we can find a closed form of that and just run the limit as t approaches infinity because we can actually get an expression for it. But as soon as we start doing these nonlinear ones, in most cases we can't even find a closed form expression for the difference equation, therefore we can't analyze that way, so we're going to use an alternate pictorial representation of this. So our function is this guy. I get rid of the star and the t's just for simplicity when I'm solving the equation, so I'm going to call f of x equal x squared minus x plus 1 the right hand side. And we seek x values such that it's a fixed point for f, or f of x equals x. Doing that explicitly for ours. Remember, there's a difference between plotting this function and setting this equation equal to 0. Doing this right here is going to give us a nice completing the square. It's going to give us x squared minus 2x plus 1 equals 0, if and only if x minus 1 squared is 0. So that gives us the unique equilibrium x star equals 1. Pictorially, once I plot those, how do I plot those? Well, this is what they were saying, and then we're going to also plot these two types of things, because then we're going to get these Cobweb diagrams to help us look at the stability of equilibria. What we're going to do is we're going to always plot on there. This one is xt plus 1 equals xt, the line y equals x, but in the xt plus 1 plane. And then the other one is plotting the function xt plus 1 equals f of xt. To do that, my function is f of xt plus 1 equals xt squared minus xt plus 1. So I had to complete the square to find what the vertex of that parabola is. The vertex of the parabola is 1/2, 3/4. And then I can plot where's the y-intercept of this guy. When x is 0, y is 1, so it crosses the y-axis here. It has no real roots, because if you look, this is positive. When I tried to bring the other side, I'll get the square root of -1, which means there's no real roots. But there's the plot of xt plus 1 equals f of xt, and the plot of xt plus 1 equals xt. Then what I do is, if there are any equilibrium, pictorially, instead of algebraically solving for this, pictorially we get that it's the intersection of those two curves. In this case, it actually happens to be a tangent point, but this is the unique equilibrium point, the x value, or the x coordinate of that intersection point of the graph xt plus 1 equals xt and the graph xt plus 1 equals f of xt. I know there's a bunch of t's going on there. Let's do another example. Example 2, we're going to find the equilibriums of the difference equation xt plus 1 equals axt plus b. Essentially, these are all constant coefficient, first order, non-homogeneous, but when it's a constant, this is the general form when we get a and b are constants. Specifically, we have to deal with the classic arithmetic sequence first. If we get rid of the b, this is classically a geometric sequence that they do in grade school. And then this one where we let a equal 1 is the arithmetic sequence. But neither of these really have equilibria. Let's look at the first one. If we look at constant growth, or xt plus 1 equals 1 times xt plus b, which means essentially if you move this over the difference equation, the difference is a constant b in every step. That's why they call it constant growth. Our function is f of x equals x plus b, so to get an equilibrium we have to have this condition, which is going to be x star equals x star plus b. That can happen only when b is 0. Yeah, otherwise something goes wrong drastically. And when we look at this, in case one of b is not 0, then there's no equilibrium is what that says. And that should make sense. When b is positive, this should be increasing. We're adding the value b every time, so it's going to just keep growing. And if b is negative, we're going to subtract off b every time, and so we're going to get decreasing for all of t. So there's going to be no steady state point. It's either going to increase or decrease, but it's never going to stay steady. So this one is relatively uninteresting. There's no steady state points. Oh, there is when b is 0, which is relatively uninteresting. What does that tell us? That just says xt plus 1 equals xt for every t. If you start at alpha, whatever alpha point you start at, they're all going to be alpha for every t. So this is relatively uninteresting. A little bit more interesting, and actually it blows up in your face really fast. We're going to have to draw to look at the stability of these eventually. We're going to have to draw 4 cases when a is larger than 1 or less than 1, and when b is larger than 0 or less than 0. So in those combinations, there's 4 different combinations of those diagrams we're going to have to draw, and each one has slightly different stability of the equilibrium. We'll get into that in a second. For now, what is the equilibrium of this? We have that our function this time is ax plus b, where a is specifically not 1. we do that specifically because this is the arithmetic one and it's trivial, but also I want to divide by that guy eventually, so I want to make sure I'm not dividing by 0. What is the equilibrium? I look at this equation, I solve for x star in that equation, and I get a unique equilibrium b over 1 minus a. This will always be the equilibrium for all of these constant coefficient linear first order. What that tells me is graphically, if I plot in this case I plotted where I have a is less than 0 or less than 1 and b is larger than 0, then we're going to get this curve and the curve xt plus 1 equals xt. Where those two straight lines intersect will be the unique equilibrium point, and it's always going to be b minus 1 over a. What we're eventually going to want to do now, and in the next couple of scenes to end the video, is we're going to look at now what is the difference, or can you see the stability of these equilibrium or unstable equilibria. And what we mean by that is, if I start now at some other value, x0, I start at some alpha point, are my values of my sequence going to tend towards that equilibrium? So are my solutions eventually going to go to that equilibrium state, or are they going to diverge away from that equilibrium state? If they do tend towards the equilibrium, we're going to call it a stable equilibrium. If all the other solutions don't tend towards it, we're going to call it unstable, and that's the two different categories, and this is the crux of stability theory. We want to know, once we can categorize what equilibria are for a difference equation, or for the continuous one, we're going to do equilibria for differential equations also, but once we can classify them, we want to look at stability analysis on whether all the solutions tend towards that equilibrium in a nice way, or whether they are just erratically blowing up to infinity or doing strange things, and we're going to call that unstable. Let's do an example. All right, cobweb diagrams. Before we do this, stability, we'll give the rigorous definition of what asymptotically stable or globally asymptotically stable or unstable equilibria are. But for now, what we're going to do is get the intuitive idea of how to see with these cobweb diagrams and a pictorial representation. Whoop, mic drop early, preemptive marker drop. All right, so what is the cobweb diagrams? I'm pretty sure they made it because it looks like a spider web or a cobweb. This one anyways, that's why I picked it. Some of them don't exactly. But what we're going to do is, first of all, step one, we're going to draw the xt and the xt plus 1 plane. And then in there, we're going to plot the functions xt plus 1 equals f of xt and xt plus 1 equals xt. So y equals f of x and y equals x are the straight line. And then in this case, I've also picked another straight line, but whatever that function is. Where they intersect is equilibria, we saw. And then now what we want to know is, do we have stable equilibria or unstable equilibria? What we're going to say is now, how do we tell that pictorially? This is quite clever. What we're going to do is, first of all, we're going to locate our initial condition on the xt axis. There he is. From the point x0, 0, this point, we're going to draw a vertical line to our function f of xt. That will put us at this point, but that point is x0, f of x0. F of x0 is x1. So this takes us to the point x0, x1. Then what we're going to do is draw a horizontal line from that point to the straight line xt plus 1 equals xt. And that's going to put us at the point x1, x1. And then what do? Repeat that indefinitely or until you give up, or you want to see a pattern on whether it's trying to converge to the equilibrium point or diverge away. If it converges to, we're going to call it stable. If it diverges away, we're going to call that unstable, roughly speaking. We'll give the rigorous definition next time. So in this one, you can see that if I start here, I go up to this curve, and then we just keep iterating it, and we see that we are getting closer and closer, and in fact, we can get arbitrarily close to the equilibrium as time goes on, and this is what we're going to call an asymptotically stable equilibrium. Let's do an example of this, specifically the one we were doing previously, and then we'll look at the two cases of this diagram where a is less than 1 and b is larger than 0, and a is less than 1 and b is greater than 0, and we'll have a stable and an unstable equilibrium from the same difference equation. And then next time we'll give the rigorous definition of what stability is for equilibrium. All right, example 3, to finish up, we're going to look at the long-term behavior of this difference equation, xt plus 1 equals a, xt plus b, where specifically a is not 1, so it's not the arithmetic sequence, and b can be any real number we want. So In this case, what I want to point out, first of all, is I picked this example because it's overkill, but then examples or more complicated systems that we get where I can't find an explicit closed form, this procedure of the Cobweb diagrams won't be overkill. For this one, using our clever methods, or go watch our previous videos, we have a systematic way, whether they're constant coefficients or non-constant coefficients. We have that horrible formula for what the general solution to is for a first order linear, non-homogeneous, non-autonomous difference equation is. In this case, it's this. Xt is a to the t alpha, our starting point, plus b a to the t minus 1 over a to the a minus 1. Once I have the closed form, I don't need this cobweb diagrams. I can actually look at and I can solve for the equilibria. I know in this case the equilibria from the previous example, we saw the equilibria was b over 1 minus a. And then I can see from this closed form, if a is less than 1, like we're going to do in the cobweb diagram, then if I take the limit as t approaches infinity and this is less than 1, this is going to go away. And so will this term, and then the negative will distribute in there, and I'm going to get that flipped around. So it'll be b over 1 minus a. And that says that for all time, if a is less than 1 and b is positive, that xt is going to tend towards arbitrarily the equilibrium point. So solutions are converging towards the equilibrium point if a is less than 1 and b is greater than 0. I can get that complete analysis from the closed form. And if I take another scenario from this closed form, if I look at a is larger than 1 and b is less than 0, then I'm going to see that this will blow up and this blows up, and long story short, it's going to diverge away from the equilibrium point. And that's what we're going to call unstable. So why would I do cobweb diagrams? Well, nature doesn't really care, and when I get real world scenarios and real world difference equations, often they're not even linear, so we don't have a way of finding the closed form solution for them. And I would still want to know, can I find, by solving these non-linear fixed point problems, can I find the equilibria, which is hard enough. Once I do have the equilibria, can you tell me the stability of those equilibria over time? And stability, we're saying, are they solutions all tending towards that equilibrium state, or are they diverging away from that equilibrium state, depending on where we start our sequence from? I know there's a lot of moving parts, but say I didn't have the closed form, or I couldn't remember how to solve that, we can still get at, we solved in the previous example, how to get the equilibrium. It is b minus 1 over a. Now, using the cobweb diagram, I plot xt plus 1 equals xt. I plot my function, xt plus 1 equals f of xt. In this case, it was a xt plus b. Where they intersect is, of course, that equilibrium point. And then I arbitrarily pick a point x0 on the xt axis, my starting point. I'm going to assume it's a positive number in this case. But either way, whether it's below the equilibrium value or above the equilibrium value, do the cobweb diagram vertically up to this line, then horizontally across, then vertically up, then horizontally across. And it looks like as each timestamp goes, I'm getting arbitrarily close to the equilibrium. And it doesn't matter whether I start above the equilibrium point either, it's still going to go towards that equilibrium. This is what we're going to call a stable equilibrium in this scenario. We'll give the rigorous definition in the next video. This scenario, though, if we do a is larger than 1 and b is less than 0, regardless of which side we start on, if I do the cobweb diagram, I see that my points are diverging away from the equilibrium, and the same if I start on the other side. And this is what we're going to call an unstable equilibrium. Next time what we're going to do is the rigorous definition of stability, and then we'll give some results on trying to find out in these nonlinear difference equations how to find global asymptotically stable equilibriums for difference equations. Please subscribe right here. I'll see you next time.